Today we're going to start to take a look at actually doing some descriptive statistics. Descriptive statistics is trying to describe the data we have, and there are several ways we can do that. One way we can describe the data we've collected is by using some type of visual display of your data, and that's what we're going to look at this week, are visual displays of data. The problem we have with data is we can collect it and display it in this nice table. Let's say I want to interview the number of coffee purchases per family last week. I survey 50 random people using one of the sampling methods we talked about last week, and I come up with this data. It is really hard to look at data and extract any meaning out of it. You could imagine how difficult it would be to extract meaning out of a table that's got thousands of data values in it. It just isn't useful as raw data. And so what we're going to do is we are going to convert this data into a meaningful form, and there's several ways we can do that. One way we can do that is with what's called a frequency distribution. This is going to be a distribution that is a summary of data, and it will display the number of observations in each of the distribution's classes. Classes. What are classes? Well, classes are just the categories in the distribution. So for the data we were looking at, the number of coffee drinks, we'll have a category that says how many people had 1 coffee drink, how many people had 2 coffee drinks, how many people had 3 coffee drinks in the week. And the classes are the categories, 1, 2, 3, 4, 5, the number of coffee drinks. What I'm talking about here works really well with what is called discrete data. Data responses that are countable. You can't have in-between values. You can't purchase half a coffee. You can't have 2.5 coffees. You either purchase 2 or you purchase 3. It's very countable. This is discrete data, and this works really well for this type of a distribution. So back to our data, what I've done is I went through and color-coded each of the responses. So this is the same table of data, but this time you'll notice it makes it really easy to see. The 4s are all yellow, so I could be able to count how many people had 4 coffees in their family. 1, 2, 3, 4, 5, 6, 7. You can also count maybe the number in green, the number of 3s. There's 2 people who had 3 coffees. And so I can go through and I can count how many responses of each type, and I can build what's called a frequency distribution. Down one column I list the number of coffees purchased, and down the other column I list the frequency, or how often those came up. So I can see the number 3 showed up 2 times. The number 7 showed up 6 times. And this can be a little more useful to us, that we can see, gee, the majority of people grouped around this larger number, 5 to 6 coffees per week. So if they're purchasing 5 to 6 coffees per week, do we want to advertise with them? What do we want to do with this data? We can decide internally whatever the reason was we requested the data. It's a lot more useful in this format of a frequency distribution. Sometimes what can help us is, instead of just looking at the frequency, we look at what's called the relative frequency. The problem with a frequency distribution is it shows us the number of times each event occurred. But without knowing how many total there were, it's really difficult to compare them directly. And so that's where relative frequency comes in, is it's going to convert those responses, the number of responses in each category or class, into a percent. So we could say 12% of people did this, 40% of people did that. And the percents are a lot easier to interpret when you don't know much about the actual collecting of the data. So what relative frequency is it's the proportion of total observations that are given in a class, often as a percentage. The way we're going to do that is we are going to divide the frequency, which we're going to represent with f, by the total number of data values, which we'll represent by n. This will give us a decimal frequency, and we're going to convert it to a percent by multiplying by 100. So we could come up with this mathematical formula that the relative frequency is the frequency divided by the number times 100. So back to our data, there were 50 observations recorded. So N, the number of data observations, is 50. And for example, in class 4, there was a frequency of 7. 7 people responded with the answer 4. So what we're going to do is find the relative frequency. We take that 7, divide it by 50, the number of data values, and then we'll multiply by 100 to get our percentage of 14%. 14% of our families drank 4 coffees a week. Let's do one other example. For class 9, we had a frequency of 6. So we take that 6 and divide by 50 times 100, and we find 12% of our families drank 9 coffees per week. And you can already tell how that's much more useful than just knowing the number of families. And we're going to repeat this for all of our classes. I picked 4 and 9 kind of out of the middle just for our examples. You'd start on the first one, calculate the percentage, then the second one, work your way down the table, and we get our relative frequencies in this third column here of each of the data values. Now this works great to make a relative frequency table or a relative frequency distribution if we've got a clear finite number of coffees being ordered. There were exactly 10. Nobody was ordering 6.5 coffees. That doesn't make sense. But in some cases, we need to go to what is called grouped data. Group data we need in one of 2 cases. One option is a continuous case, where the data is not discrete. Remember, discrete means countable. Grouped data could be used for continuous or uncountable data. That can be any value in between. Let's say we're doing some type of measurement, and we want to know how tall a building is. That building could be 12 feet tall. It could be 13 feet tall. It could be 13.5 feet tall. It could be 13.21689 feet tall. It can be any data value in between. That is continuous data. You can't count all the possibilities because there's always something else in between those values. We can also stretch group data to discrete values with many possible results. For example, if we're talking about the weight of our customers, we want to make sure that some type of chair that they're going to be sitting in can support their weight. If we record their data as discrete values rounded to the nearest whole number, we could have a really light person that's 110 pounds, or we could have a person that's on the other extreme, maybe over 300 pounds. There are lots of values in there, and we don't want to make our chart cover every single weight. 110, 111, 112, 113, 114, 115. That's going to not be any more useful than all the spread out data. And so we're going to group those data values together as well. So that's where we want to use grouped data. So here's some more data. We got the weight of 50 of our customers here. It's all over the map. And we want to make a frequency distribution. Now there's probably too many unique individual numbers. We're not just going to list, well, there's some people that are 128, some people that are 129. That's just not useful. So we're going to break them into classes of equal width. In other words, we're going to have a range, maybe 150 to 160, and we'll group all of those people together. That's how we're going to build this frequency distribution. However, we want a systematic way to do it to make sure that we are accurately reflecting the data we collected. So first we need to determine the number of classes or the number of groups or bins we're going to use. There's no hard and fast rule that you must do it this way. Usually people pick between 5 and 20 different groupings for their data. Now, some people really like to have a formula. How do I determine? Do I do 5? Do I do 10? Do I do 7? So one method that's kind of out there is you look at this expression, 2 to some exponent. You want to be less than the number of data values. So in our case, we've got 50 data values. So we want 2 to some exponent to be less than 50. And you can kind of just guess. Let's guess 2 to the 6th power. Well, 2 to the 6th power is 64. That's more than our 50 data values. So we'll go smaller than 6. 2 to the 5th power is 32. And that is less than our 50 values. So because 2 to the 5th power is less, we're going to use 5 as the number of classes. We're going to group our data into 5 groups. Now that we know we have 5 groups, we need to determine the width of each class, or how big is each group going to be. To do that, we use this formula, that the width is equal to the largest number minus the smallest number divided by the number of classes that we're working with. Remember, we just decided we were doing 5 classes. So for our data, 202 is the largest number. 118 was the smallest number. And you can look through your data and you can find those values. 202 minus 118 is 84. And then we divide by the number of classes. We decided there'd be 5. 84 divided by 5 is 16.8. To make life easier, we're going to round that value. And we always round up with our bin widths. Always round up to 17 in this case. So each class is going to be 17 large. 5 classes, 17 large. So let's determine the boundaries. What range is going to be in each group? We'll start with our smallest value of 18. And we're going to add 17 to get the next starting value. 118 plus 17, the next group starts at 135. So we see 118 plus 17 is 135. Plus 17 is 152. Plus 17 is 169. Plus 17 is 186. Then these other numbers are just one less. If we 135 minus 1 is 134. It's kind of the break off. 135 goes through 151 because 152 is on the next row. Through 168 because 169 is on the next row. And now we've got our 5 groups. We just have to go back to our data and actually count how many people were between 118 and 134 pounds. There were 4. There were 11 people who were between 135 and 151 pounds. There were 26 between 152 and 168. There were 7 between 169 and 185. There were 2 between 186 and 202. And we now have our frequency distribution for our continuous data. We do classes of equal widths. We group the data together. We could even take this one step further and figure out the relative frequency if we wanted that information. Again, we just take the frequency divided by the number of data values. There were 50 again, so 4 divided by 50 times 100 is 8%. 11 comes 22%, and so on and so forth. We can find the relative frequency of each of these groups. Another visual way to demonstrate your data and your results is using what is called a histogram. Now, a histogram has a large advantage over the relative frequency distribution. Going back, our relative frequency distribution, it's really hard to compare our numbers. We can see it's going up and then it goes down, but it's really hard to compare how much more and how much less each data value is. And what a histogram is going to do is visually represent the frequency of each bin, of each class. visually will make it easier to compare how much more each class is, each group is. A histogram is a graph of a frequency distribution. The horizontal axis shows the classes, and the vertical bars have a height that reflects the frequency. Some people call these bar graphs, and that's actually inaccurate. I don't want you to call this a bar graph, but it's similar in that you've got vertical bins, we call them, showing how often or how frequently they show up. What's important to note is we use histograms with quantitative data, with answers that are inherently numerical. They must be quantitative, numerical. So let's say I'm interested in a phone company. I call them. They say, your call is important to us. Your expected wait time is. And we look at 200 service calls. And we record the number of seconds that each person had to wait before they got service. How fast could we get to them? And as you can tell, just looking at this data, it's very useless in this form. Raw data is generally very useless. It's hard to make any conclusions. How long are people waiting? I don't know. So, first, to make a histogram, we need to know the frequencies. So let's make our frequency table. We need to know the number of bins, or the number of classes. So we take 2 to several exponents. We mentioned that we've got 200 data values. So we want 2 to some power to be just under 200. 2 to the 6th power is 64. 2 to the 7th power is 128. 2 to the 8th power is 256. 256 is too big. We only have 200 data values. So 2 to the 7th, we want 7 bins. Okay. How wide do we make our bins? To figure out the width of our bin, we take the largest minus the smallest. So the smallest wait was 25 seconds. The longest wait was 278 seconds. So for our bin width, 278 minus 25, divide by 7, we get 36.03, and it goes on. Okay. We need to round this up to 37. So we've got 7 bins with a width of 37, starting with the smallest value of 25. So here's our 25, plus 37, plus 37, plus 37, plus 37, plus 37, and plus 37 gives us all of our data values. Then we go back and we add up and count our frequencies. Probably with 200 data values, you're going to want to use some software to help you count the frequencies. We're going to look later at how we can use Excel to help us do that. But for the sake of time, I've already gone through and counted each class and how often they appear. We're going to convert this frequency distribution into a histogram. So for the histogram, the horizontal axis has to represent our data values. And notice the numbers I put on the horizontal axis are the starting points of each bin. 25 plus 37 is 62, plus 37 is 99, plus 37 is 136. They're all those lower limits from our frequency table. 25, 62, 99, 136, 173. Going up the vertical axis then is just our frequency, how often they appear. Because our data values range from 6 to 116, I decided to count by 20s going up. Frequency has to be vertical on a histogram. Then what we're going to do is we're going to make a bar to the right of each number showing the frequency. So the 25 to 62 showing the frequency up to there. Then we look at our data, 62 to 99 appeared 41 times. So we make our bar going just over 41. And we keep going, 99 to 136, 136 to 173, 173 to 210, to 247, and to 284. Notice as we make this histogram, the bars touch each other because they are showing how many data values fall within the range of 99 to 136, just under 100 we can see here. Because the bars are touching each other, we know there is no gap in our ranges. Histograms, the bars must touch. Unless there's actually 0 data values for some reason. But other than that, the bars must touch. Now we can look at this histogram and make some conclusions. We can see that it's almost split in half. Half of our customers are 136 and below, 173 and above is the other group. Kind of clustered around the middle. Most people are between 136 and 173 seconds of wait time. That's less than 3 minutes. That's actually pretty good for waiting on hold. So this company seems to be doing all right. Histograms. Another type of visual display of data is what we call a bar chart. And bar charts are often confused with histograms. So let's split this up and really look at why they're different. A bar chart represents categorical data with a bar over each class. Because it's categorical, it is quantitative. We don't have answers like 1, 2, 3, 4, and 5. We have answers like blue, red, green, and orange. They're categories. And in these categories, the bar represents how often each category shows up. We don't have a range of numbers anymore. So for example, we could look at the number of car sales for each of the top car companies out there. So let's say these are their sales. We can make a bar chart with a bar for General Motors, a bar for Ford, a bar for Chrysler, a bar for Toyota, and the height of the bar is the number of sales that they each had. And so by doing that, in much the same way as the histogram, we get a bar for each category. Notice these bars do not touch. In a bar chart, the bars cannot touch because we're not covering a range of data. Each data value is completely separate and independent. One other type of visual display that I want to take a look at is the line chart. And a line chart is a two-dimensional graph that shows how some variable changes over time. And we put the changes in time across the bottom, across the horizontal axis, and then the height is what that variable is doing over time. And so once you have your axis set up, you just plot each data value and then connect the dots with straight lines. And you've probably seen these graphs before. They're pretty straightforward. A common line chart you might see is unemployment. Looking at unemployment from July 2008 through June 2009, that's a 12-month period. Over that year, unemployment went from 5.8% to 9.5%. So let's make this chart. What we'll do is the time is going to go across the horizontal axis. Unemployment values are going to go across the vertical axis. And we can end up with this line chart. Notice the line chart puts the time across the bottom. In this case, it's months. It might be years. It might be seconds. It might be days, whatever your situation. And then we put a dot in July. Unemployment was right here, just under 6%. August, it was just over 6%. And so on and so forth. And then we connect the dots with straight lines, and you can see there is a definite upward trend in unemployment, almost a linear growth in unemployment. And so that's kind of our visual displays of data. We've seen several different ways to display data visually. We started out with still using numbers, but a frequency distribution to kind of show how many responses we had in each category. Then we took that frequency distribution and made it even more useful by finding the relative frequency distribution to find the percentage that fell in each category. And we did that by taking the frequency, dividing by the number of data values, times 100 would give us a percent. Then we stretched it further to uncountable data responses. Uncountable such as weight. There's so many different data values. It might be some type of continuous measurement, the height of something, the width of a pipe, whatever you're working on. And so we would group data together in such a way that we could represent the frequency of a group. And the groups are called classes. And the way we determine the number of classes is we said 2 to some power has to be smaller than the number of data values. And we would just try numbers, try 6, try 7, until you ended up bigger than the number of data values. And so it's the largest one, the largest exponent that stayed smaller than the number of responses. And that told us the number of classes, and then we could find the width by taking the largest number minus the smallest number and divide by the number of classes, and always round that up. After we saw group data frequency distributions, we started looking at some visual options. One option was the histogram. An important characteristic of histograms is the bars touch. They are for quantitative data, where you have numerical responses. We also talked about bar charts, which the bars do not touch. They are for categorical data or qualitative data. And then finally, we looked at line graphs to show change over time. Your homework assignment is going to take a look at each of these distributions, and then we'll look at how we can make these distributions in Excel in another video.